Hey everyone, welcome back to my channel. So like I promised you, a new year, this video is about farm equations, and stay tuned for the next video about the menstrual cycle, and don't forget to share the channel. And so today in this video I'm going to talk about volume of distribution equation, the clearance equation, and the t-half equation. And you might look, oh my god, I'm gonna memorize all these equations, but in this video I'm gonna teach you how to derive the equation without having to memorize it at all, like derive it just from your understanding. And also we're gonna do some UWorld questions to reinforce stuff. So let's get started. Alright, so before we talk about each equation, I like to outline a big picture in my head, so that, like, if you give any drug, like if you inject any drug inside your body, it doesn't just stay in one place. Like, it's gonna, like, some of it's gonna be in plasma, but then it's gonna distribute elsewhere to other organs, and that's called distribution, which we're gonna talk about with volume of distribution. And also some of this drug is gonna go to the organs of excretion, and so it's gonna be cleared, for example in the kidneys, and that we're gonna talk about in clearance. And remember that the drug doesn't just stay forever in your body. Like, at one point it should go away, and so the time period that we measure how much the drug stays in your body is called the half-life. And so that's essentially all about pharmacokinetics, and that's what we're going to talk about today. Alright guys, before we talk about volume of distribution, I like to derive the equation right away from the rules of physics. So imagine I have 3 milligrams of drug highlighted by 3 points, okay? So imagine those 3 dots or 3 circles are 3 milligrams of a drug. That's my amount, alright? Or dose. And I like to dissolve these 3 milligrams in 1 liter of water. Okay, and so I have 3 milligrams and I dissolve them in 1 liter. I should get a concentration of 3 milligrams per liter. That should be your plasma concentration of the drug, right? And so imagine that I do not know this volume at all. Like, I don't know how much volume I dissolve this drug in. And how can I possibly derive that? How can I possibly figure that out? Simply, if you go back to physics, volume is amount over concentration. Alright, and so if I want to calculate the volume of distribution, I should very easily derive it from the fact that I have the drug dose in milligrams, and I have the drug concentration in plasma in milligrams per liter, and so I can figure out the volume of distribution in liters by dividing the dose in milligrams by the concentration in milligrams per liter, right? And that's essentially the equation of volume of distribution, okay? So in order to understand that each drug has a different volume of distribution, you gotta figure out something, that once you give the drug, the features of the drug will determine whether it's going to stay inside the intravascular compartment or it's going to distribute elsewhere to the intracellular or interstitial compartment, or it's going to bind fat. All that depends on the characteristics of the drug. So let's say we have drug A, okay? So drug A is the first type of drug we're going to discuss. And I want you to count those blue dots. You find there are 6. So let's say I injected 6 milligrams of drug A. Okay, so because drug A is so hydrophilic, or like charged, or it's so big, or it's highly bound to plasma proteins, that's albumin, it doesn't like to distribute so much. It just want to stay in plasma because it can't go elsewhere. It's confined within the plasma, and so all the 6 blue dots are going to stay in the intravascular compartment, which is going to give a very high plasma concentration. because the entire dose of the drug that I gave just stayed in there and didn't go anywhere else. And that results in such a low volume of distribution. So this is one type of drug we have. All right. Now, another type of drug will be drug B. Drug B is kind of a little bit in the middle. It is hydrophilic, which means it will not be able to cross the cell membranes into the interstitium, but at the same time, it's small, which means that some of it is going to stay in plasma, but it's small enough to get out of the blood vessel and actually distribute in the interstitial compartment. And so out of the 6 milligrams I gave, 3 are going to stay in the plasma and the rest are going to stay elsewhere in the extracellular fluid. And so the plasma concentration is a little bit lower than drug A, and so this is going to have a higher volume of distribution than drug A. It did distribute a more extent than drug A did, right? And finally, drug C would be the smallest and most lipophilic of all of them, and it doesn't want to stay in plasma at all because it's so small and just wants to mingle around, and so it's going to distribute the most. And so if you take a look at drug C, you're going to find it everywhere else but the plasma. Imagine, so its plasma concentration is going to be very, very low, and so its volume of distribution is going to be very, very high. And it's logical, actually, that if it distributes everywhere else but the plasma, then obviously it's going to be everywhere else in the body, but its plasma concentration is very low. So the fact that the plasma concentration is very low means that it has distributed a lot and that it has such a high volume of distribution. Okay, now let's put that into numbers. Here is the picture of body fluid compartments. Total body water we know is 42 liters. Total body water, 2/3 of it is intracellular, that's 28 liters. 1/3 of it is extracellular, that's 14 liters. And of this extracellular volume, we have 4 liters of plasma volume, and the rest is interstitial. So if a drug like drug A likes to stay in plasma alone because it can't distribute anywhere else, then its volume of distribution would range around 4 liters, right? However, a drug like drug C, for instance, that likes to stay everywhere else but for the plasma, which means that it can distribute everywhere, essentially everywhere, it can reach the entire total body water if it's that small and that lipophilic and just mingling and crossing cell membranes. And so if you want to put that into, that's essentially how questions would come. They will give you numbers. All right, and so let's practice a question to reinforce that. All right, guys, so here's a typical question about volume of distribution. So a new aminoglycoside antibiotic is developed that is believed to be particularly effective against Pseudomonas. The volume of distribution of the drug is measured in a group of volunteers and is determined to be 4.5 liters. This new drug is most likely to have which of the following properties? Now, this question is very easy. You know why? Because it gave you 2 clues on the property of the drug. So you could answer this question in 2 ways. Either because you realize that aminoglycosides are hydrophilic, and you might, like everybody knows that, but you might not. And another way to solve this question is to recognize that 4.5 liters is a relatively low volume of distribution, which is essentially the plasma volume. So if you realize that 4.5 liters means that this drug is primarily contained within the plasma compartment and hasn't left the plasma compartment, then this drug must be highly charged, right? None of these other answer choices is like correct. Low molecular weight will actually escape this compartment and distribute elsewhere and would have a higher volume of distribution than this, same as if it if it were lipophilic as well. And It does not bind albumin. It's actually the other way around. It's when the drug is highly bound to plasma proteins that it would display low volume distribution, as it would be restricted to the plasma, right? And so the only correct answer here is that it's highly charged and therefore is maintained within plasma with such a low volume of distribution. Now, high oral bioavailability is a little bit irrelevant. High oral bioavailability means that a lot of what is taken in or ingested reaches the blood or reaches the plasma, and this really has nothing to do with distribution. Okay, and so the correct answer is highly charged, and I'm surprised actually that not a lot of people did it right. It's like 39%, even though this question gives you two clues, guys. You either know that aminoglycosides are hydrophilic and hydrophilic drugs have low volume distribution, or that we recognize that 4.5 liters is a bit low, and that means it's maintained within the plasma compartment, and only the highly charged drugs are maintained within the plasma compartment. Okay? Next up, we're going to talk about clearance. And once you look at the equation for clearance, again, you might be scared that you'll have to memorize that, but I'm going to show you a way to derive it just like we did for volume of distribution. All right, guys, so our approach to clearance is a little bit similar to volume of distribution, but I like to remember that clearance is a rate, as in it's not just liters as in volume of distribution, rather it's liters per minute, okay? It's bound by time, okay? It's not just volume, it's volume per unit time. And so if you actually remember the definition, clearance is the volume of plasma cleared of the drug per minute, okay? And that's how fast your body is capable of clearing plasma of the drug. And so if we take if we start an experiment and we have, this is plasma and it's got 5 milligrams per liter of drug, that's plasma concentration. All right, and your body is capable, or your kidneys or your liver, whatever excretory organ we're going to talk about, is capable of clearing as a rate of elimination, is capable of eliminating 5 milligrams every minute. All right, and so what is the clearance rate based on these values? If your body is capable of removing 5 milligrams of the drug every minute, and you have given this body a plasma full of 5 milligrams per liter, then you have essentially cleared an entire liter of plasma. That's clearance rate. Okay, so I give you 5 milligrams per liter and you're capable of removing 5 milligrams every minute, then you have cleared 1 whole liter of plasma. That's what we mean by clearance rate, and it's in liters per minute. Okay, and so if we go back to the same notion of volume being equals to amount over concentration, it's going to be the same as in volume of distribution. So but in this case it's going to be amount per minute. So clearance in liters per minute equals amount cleared per minute, milligrams per minute, over concentration, plasma concentration of the drug in milligrams per liter. That should give you a rate in liters per minute, which is clearance. All right. All right, the final equation we're going to talk about today is half-life, and I put that in the end because half-life depends on two factors: volume of distribution and clearance. Okay, so it's essentially the time that's it's defined as the time taken for the drug to drop in half, but I like to think about it as how long the drug stays in your body. Okay, so how long the drug stays in your body depends on how far it distributes, like the extent of its distribution, which is the volume of distribution, and how quickly it is cleared, which is the clearance rate. And so these are two logical factors that affect how long the drug stays in your body. And so let's say we increased the volume of distribution but kept clearance the same. Okay, so clearance is the same, but the drug is just so extensively distributed in your body that it will take so much time from us to get rid of it, even though, like, if we fix the clearance rate, but the drug distribution is just a lot, that means we're going to stay for a whole lot of time to get rid of it, and so that should increase the half-life. That's if we increase volume distribution while clearance is constant. Another thing we can do to change the half-life is to change the clearance. Okay, so imagine the volume of distribution is kept unchanged, so the extent of distribution of the drug inside the body is the same, but we increased the clearance. Okay, and so we increased the rate of getting rid of the drug. Okay, so if we don't change the volume distribution but we get rid of it faster, then it shouldn't stay around for long, and that should decrease the half-life. So these are the two factors that affect drug half-life: volume of distribution, the more, and clearance, the more, the less. Okay, so let's do a UWorld question to reinforce that. Alright guys, so here is a typical half-life question, and I like to read whenever I find a lot of numbers here. I figure out that this is a calculation question, so I don't need to read the entire history just for the purposes of this video. So the question wants, which of the following is the most likely serum drug concentration just before the next dose 8 hours later? So it's essentially asking us for concentration, and that is why the units here are in milligrams per liter. Alright, so I like to focus on the numbers given and the units, and you jot them down in your scratch paper and do your calculations based on the equations you know. And so as part of this patient's treatment, 240 milligrams of intravenous gentamicin is started, and so this is the dose, 240 milligrams. Alright, and so I go to a whiteboard and I write dose given IV is 240 milligrams. Okay. Back, the pharmacy calculates that in this patient, gentamicin has a volume of distribution of 30 liters. Okay, so your volume of distribution is 30 liters. And a half-life of 4 hours. And so this is what's given to me right now. The T-half, 4 hours. So these are the numbers given. What does he want? He wants serum drug concentration after 8 hours. And you should figure out right away that 8 hours is double the 4 hours. So what the examiner wants is the serum drug concentration after 2 half-lives. All right? And it's important to note that this drug demonstrates first-order kinetics, and that's to show you that the half-life is constant, and you should calculate it as 8 hours is 2 half-lives. All right. As we mentioned all along, we know that volume equals amount over concentration. Right? Now, we don't have the concentration. That's what we want. We have the volume of distribution in liters, and we have the amount of drug in 240 milligrams. And so if you put 240 milligrams in 30 liters, you should get a concentration of 240 over 30, right? Milligrams per liter. So that should be 8 milligrams per liter. All right, you put 240 milligrams in 30 liters, you get 8 milligrams per liter. Okay, that's milligrams dose per volume in liters. Very good. So now I have the starting concentration. The starting concentration is 8 milligrams per liter. Now, let's say 1 half-life elapsed, 4 hours elapsed, and after 4 hours we reached 4 milligrams per liter, half the A. After another half-life elapses, another 4 hours elapses, this 4 becomes half, which is 2 milligrams per liter. Alright, so after 2 half-lives, which is 8 hours, so that first 4 hours, 8 became 4. Next 4 hours, 4 became 2. So after 8 hours, I dropped from 8 to 2. And that's exactly the correct answer of this question. So those 8 hours later, the clue here is to recognize that 8 hours is 2 half-lives. And the other clue, the other key to answering this question is to know the amount over volume gives initial concentration. Alright, so almost everyone got this question right. About like quarter of people got it right, because you just need to jot down your givens, alright, and recognize that concentration is amount over volume and that 8 hours is 2 half-lives. Okay.